You know, when we had chain rule, it gave us a way that we could take the derivative of quantities. Substitution rule is going to be the answer for that in integration. It's going to give us a way that we can integrate when we have a quantity. Now, before we can do substitution rule, we need to go back and review a concept that we learned a little while back, and that was the idea of differentials. I think it was maybe section 310, perhaps. But when we worked with differentials, the idea was if I had a function like u is equal to 1 plus x squared, we would go through and we would take the derivative of u. And since that function was in terms of x, we would write it as the derivative of u in terms of x. So the derivative of 1 plus x squared would be 2x, so the derivative of u in terms of x was 2x. In a differential, we literally think about this derivative as a fraction that can be separated and treated as two separate pieces. So when we did that, we would go through and we would multiply both sides by dx so that we could solve for the differential du, and we would get du is equal to 2x dx. So it's important that we remember that because we're going to need that for a good part of what we're doing in our lesson today. All right, so we get to example number 1. And we've got the integration of the square root of 1 plus x squared times 2x dx. I have a problem. I do not have a rule for integrating a quantity under a radical. If this was just the square root of x, I'd be fine. But this is the square root of 1 plus x squared. I can't do that. I have another problem. I have the square root times 2x. I don't have a product rule for integration. So as this stands right now, I can't integrate it. So what I want to do is I want to try to replace the part of this problem that's causing me trouble. I want to substitute it out. So the first thing that I see that's causing me trouble is that quantity under a radical, because I don't know how to do that. So I'm going to substitute that out. I'm going to let u be equal to 1 plus x squared. All right? We've said before, like when we were working with limits, sometimes we would use u substitution, and we said you can't replace one of the variable x's with a u without replacing all of them, right? The same thing is going to be true for our integration. If I'm going to replace this x with a u, then I got to come over here and replace these x's with u's. And I'm going to have to change dx to du, because if I'm integrating in terms of u, then I need a du down here. So I need to know what du is equal to. Du is literally the differential. And so that takes us back to the work that we did over here. Du is equal to 2x dx. So I can come over here and say, okay, du is 2x dx. So now let's see if we can substitute. If I come over here and I replace the square root of 1 plus x squared, since u is 1 plus x squared, that would just be the square root of u. And then I can replace 2x dx with what it's equal to. 2x dx was du. So I have the square root of u du. Now that I can work with, because the square root of u is u to the 1/2. So I've taken an extremely complex integrand, and by substitution, I've made it much simpler, and I've made it something that I can work with. All right? So then I could go through and say the integration of u to the 1/2 is going to be, add 1 to the 1/2, and I get 3/2. So that would be u to the 3/2 divided by 3/2, and of course dividing by 3/2 is the same as multiplying by 2/3. And because this was indefinite integration, I do need my arbitrary constant plus c on the end. I was the one who chose to put the u in the place of x, so when I get to the end of my problem, I need to back substitute and put that x back in the place of u. So I'm going to put 1 plus x squared back in the place of u. And that'll be my final answer. Now, we get the idea that this is just a little bit of a contrived problem, right? I mean, what's the chance that when I do my differential du that what I get just so happens to be exactly what's sitting here in the problem to be replaced, right? That won't always be the case, but for these first couple, they are going to let us have the setup that we need. All right, look at the next one. For the next one, we've got the integration of 3 cosine 3x dx. What is causing me a problem there? What can I not do?
3x dx.
Yeah, I can't do the 3x. I don't know how to integrate the cosine of a quantity. I know the integration of cosine x, but I can't have anything else with that x. So since that's what's causing me trouble, I'm going to substitute that out. I'm going to say, let's let u be equal to 3x. Now, if I'm going to replace this x with a u, then I have to replace every x with a u. So that means I'm going to have to replace dx with du. I need to find the differential du. Okay, so let's find that differential. To find the differential, if u is equal to 3x, then the derivative of u would be in terms of x. So I'm going to say the derivative of u in terms of x, and the derivative of 3x is 3. So the derivative of u in terms of x is 3. Now to just get that differential du by itself, I'm going to multiply both sides of that by dx, and so du is 3 dx. So my differential du is 3 dx. Alright, so now that we know u and du, then let's come over here and see what we can do with this. Alright, I could go through and say 3x is u, so let's replace that 3x with the u right there. So that leaves me cosine u. Now what's left over is 3 dx, and 3 dx is equal to du. So I'm going to replace the 3 dx with du. So one more time, u is equal to 3x, so I'm going to have cosine u. What's left over is the 3 dx, and 3 dx we found was the differential du, so I'm going to replace 3 dx with what it's equal to, du. One of the most common mistakes that students make is they just replace dx with du. I can't just come in here and change that x to a u. I literally have to solve for what du is equal to and replace it with what it is equal to. Notice that du does not equal dx. Du equals 3 dx. I have to calculate that differential and replace it with what it's equal to. Alright, so now that we've got our substitution, now we're ready to integrate. So what's the integration of cosine? Sine. So we would have sine u, and then this is indefinite, so we have our arbitrary constant plus c. And then I was the one who chose to put in u, so I have to back substitute and take it back out. So I'm going to put 3x back in the place of u. So we'll have sine 3x plus c. All right, look at the next one. This is actually example 1 in the book. So for example number 1, we've got x cubed cosine x to the 4th plus 2 dx. So there are actually a couple things causing me trouble there, but what do you think is causing me the most trouble? Let's try that. All right, I heard x cubed and I heard x to the 4th plus 2. And actually both of those are a problem, because I don't know how to take the cosine of a quantity, just like we saw over here a second ago. I definitely have a problem with that. And I could take the integration of x cubed, but not if it's being multiplied by something else. So we're going to talk about this in just a second, but the trickiest part of this is figuring out what to choose for u. And we're going to talk about some strategies of how to figure out what to choose for u. But for right now, let's try x to the 4th plus 2, because we know we can't, we can do the integration of x cubed, but we can't do the integration of the cosine of a quantity. So that's definitely a problem. Let's try and get rid of that. So I'm going to let u be equal to x to the 4th plus 2. So I'm going to have a u right here. If I'm going to replace this x with a u, then I'm going to have to replace dx with du. And I'm also going to have to replace this x over here with a u. All right, so let's calculate what du is equal to. So I need to find the differential. If I take the derivative of u, it's in terms of x. So if I take the derivative of u in terms of x, the derivative of x to the fourth would be 4x to the third, and the derivative of 2 would be 0. So the derivative is 4x to the third. I need just the differential du. So to get du by itself, I'll multiply both sides by dx, and I'll get the differential du is 4x to the third dx. So the differential du is 4x to the third dx. Again, I do not just replace dx with du. I have to actually calculate what the differential du is, and then I have to replace that. Okay, so here's what we've got. We've got this is u, so that would take care of cosine u, but then I need to replace dx with du, and I need to replace this x cubed. If you'll notice, du was 4x to the third dx. Ooh, I got an x to the third dx. I just don't have a 4. Okay, get rid of the 4. If you've got 4x to the third dx, couldn't you divide both sides by 4 to get rid of it? If I do that, then I've got 1/4 du is equal to x to the third dx. So I could replace x to the third dx with 1/4 du. So here's what we've got. I'm going to put u in the place of x to the fourth plus 2. So that would give me cosine u. And then x to the third dx was 1/4 du. So I'm going to replace x to the third dx with 1/4 du. All right, let's go all the way back to the beginning of that problem and go through that one more time, because this is the first time we didn't have a perfect match for what we needed, right? Okay, so let's look at it one more time. When we started off with this problem, we said what's causing us the most trouble, we got several issues, but what's causing us the most trouble is that I cannot take the cosine of a quantity. I'm going to get rid of that quantity. If I replace this x with a u, I have to put this in terms of du. So I need to go solve for the differential du. So we said the derivative of x to the fourth plus 2 was 4x to the third. That was the derivative of u in terms of x. So to get the differential du by itself, we multiplied both sides by dx. And so that gave us du was 4x to the third dx. So then we went back to our problem and we said, okay, this guy right here is u. So cosine u is set. But I also need to replace x to the third dx. I don't have just an x to the third dx over here. I have a 4x to the third dx. So I got to get rid of that 4. So we could divide both sides of that by 4, and x to the third dx would be 1/4 du. So I can go through then and literally piece by piece, I can start with this piece right here and say this is u, so that's going to be cosine u, so bring it down. What's left is x to the third dx, and we just found that x to the third dx was 1/4 du. So I'll replace the x to the third dx with the 1/4 du. So I have substituted out every single piece in this integrand. This was u, this was du. Oh, sorry, 1/4 du. All right, now I can get that constant out of my way. So move the constant out in front, just like we do with any type of integration, and I'm left with just the integration of cosine. So as we saw with the last example, integration of cosine is just sine. And then I need to back substitute my u. All right, on the bottom of 357, it says, the idea behind the substitution rule is to replace a relatively complicated integral, yeah, that's definitely relatively complicated, with a much simpler integral. This was so much easier than what I started with. That's accomplished by changing from the original variable of x to a new variable u that is a function of x. So we switch this from being in terms of x to being in terms of u that's a new variable that is a function of x. The main challenge in using the substitution rule is to think of an appropriate substitution. Here are some things that we can do to maybe improve our chances of doing that correctly. You should try to choose u to be some function in the integrand whose differential also occurs in the integrand, except maybe for like a constant factor. All right, here's what they're saying. I want to choose something from my integrand, like we chose x to the fourth plus 2, whose derivative is also sitting in your integrand. The derivative of x to the fourth plus 2 was 4x to the third. That derivative, x to the third, was sitting right there in my integrand. The differential x to the third dx was sitting right there in my integrand. So it says, try to choose u to be some function in the integrand whose differential also occurs, except for perhaps a constant. Remember that when we took the derivative, we didn't just get x to the third dx, we got 4x to the third dx, but we saw a constant can be easily addressed. We can divide it out and get it out of our way. So we don't have to have a perfect match with the constant, but the rest of the derivative would have to match. I would have to have x to the third, or the rest of the differential x to the third dx would have to match. I had to have the x to the third dx. I didn't have to have the 1/4. So that's the first thing they suggest as a way to help me choose the appropriate substitution. If that is not possible, try choosing u to just be some complicated part of the integrand. So that's what we had done on the first couple of these before we kind of had a feel for what we were doing. We just went in and looked at the problem and said, what is causing me grief in this thing? That's what I want to substitute out and get out of my way. So that's another strategy. And it says finding the right substitution is a bit of an art. It is not unusual to guess wrong. It literally is a flat-out guess. When you're trying to figure out what u should be, there's no definitive way of doing that. They gave me some suggestions, but it is nothing more than a guess. So I'm going to guess what I think u might be, and if it's not right, it says if your first guess doesn't work, try something else. So if you guess a value for u, like if we had guessed x to the fourth plus 2 and it didn't pan out, okay, try something else from your integrand and see if that works. So, just try a couple of things. So again, their suggestions are, look for a substitution whose differential is also in your integrand, or look for the part of the integrand that's just really complicated, that's causing you trouble, causing you grief. And number 3, if it doesn't work the first time with what you guess as your u substitution, try something else. Okay? So if at first you don't succeed, try again. Okay, so there on the top it says see page 357. That's what we're talking about, is that discussion that we just had on the bottom of 357 that continued over to the top of 358. All right, look at example 3. For example number 3, I've got this integral. What do you want to try for u substitution? Again, just a guess, but what do you want to try? All right, 1 minus 4x squared. We've seen that we can't integrate a quantity under a radical, right? So that's a good guess. It may not be the right one, but we'll try it. If I take the derivative of 1 minus 4x squared, what would I get?
8x.
Negative 8x. And if I did the differential, then I would get negative 8x dx, right? So other than that constant, the negative 8, my x dx, my differential, is sitting in my integrand. So that's a good sign, right? Because remember they said try and choose a u substitution whose differential is also in your integrand. So that probably means we're on the right track, but let's just see. Okay, so let's go through and do our substitution. We said that we wanted this down here to be u. So that's just going to give me the square root of u. That means I got to replace these other x's with u's as well. So we found the differential du was negative 8x dx. I have an x dx. I don't have a negative 8x dx. So I got to get rid of that negative 8. How do I get rid of that negative 8?
Divide by negative 8.
Divide by negative 8. So I'll get x dx is equal to negative 1/8 du. So I can replace this x dx with negative 1/8 du. So that whole numerator, x dx, became negative 1/8 du. And then down here, what was under the radical was what we used for our u. So again, x dx, by definition, was negative 1/8 du. And then down here, this is what we chose for our u, so square root of u. All right, so we took an integrand that was very complex and we've made it much simpler. That was our goal. Let's get that negative 1/8 out of our way. We can move it out to the front as a constant. And I'm also going to rewrite the square root of u as u to the 1/2. So I can use power rule. And I'm going to move it up to my numerator. So I'm going to write it as u to the negative 1/2. All right, so what's the integration of u to the negative 1/2?
U to the 1/2.
Yes, u to the 1/2 divided by 1/2. So that would be the same thing as u to the 1/2 times 2 over 1, right? We could say negative 1/8 times 2 and get negative 1/4. And then we just need to back substitute where we put that 1 minus 4x squared back in the place of u. And there's our final answer. All right, for example number 5, I went ahead and just wrote this whole problem out into your note sheet so that you wouldn't have to be going back and forth and trying to take notes and follow the example at the same time. So let's look at this one together. All right, so we start off with this guy. And the first thing that I see is the square root of a quantity. I know I can't do that. I'm going to try that as my first guess for my u substitution. That may not be right, but that's what I'm going to guess. So I'm going to let u be equal to 1 plus x squared. So if I'm going to change this x to a u, then I'm going to need this to be in terms of du. So I need to find the differential du. So I'm going to go through and say the derivative of 1 plus x squared is 2x. And so then the differential du would be 2x dx. Okay, so I come over here and I look at what I have. This is taken care of because that would be the square root of u. I'm okay with that. And I have a x dx over here, but it's not x to the first dx, it's x to the 5th dx. I don't need 5 x's, I need one of them. So I'm going to separate out one of my x's. There's the other 4 of them right there. I had 5 of them, right? So I'm going to separate one of them out, and there's the other 4 of them right there. So, okay, I've taken care of this. This is the square root of u. Now I've got my x dx. This was 2x dx. X dx is about as close as I can get to that, so I'm going to divide both sides by 2 to get that 2 out of my way. And I can replace x dx with 1/2 du. So there's the 1/2 right there, and there's the du. But I still have this x to the 4th right here that's a problem. And that's the first time that when I did my u substitution and my du differential that it didn't take care of everything in my integrand. All right, I'm going to go back and look at somehow what I have here has to help me. If u is equal to 1 plus x squared, I could solve that for x, right? If I solve that for x, subtract 1 from both sides, x squared is u minus 1. I have x to the 4th up here, so if I write that as x squared times x squared, I can replace x squared with what it's equal to, u minus 1. Replace x squared with what it's equal to, u minus 1. All right, so now that we've gotten all of the pieces of our integrand switched over to u's, I have some simplifying to do, right? Because I can't multiply these guys. So I need to see if I can simplify that to get rid of the products, because I can't integrate things that are being multiplied. So let's go through and let's FOIL u minus 1 times u minus 1. So that would be u squared minus 2u plus 1. Then I've still got that square root of u out in front. I'm going to write that as u to the 1/2 so that I can distribute. Remember that when your bases are the same and you're multiplying, you add your exponents. So I'm going to say 1/2 plus 2, and that would give me 5/2. Same story here, 1/2 plus 1 is going to give me 3/2, and then here u to the 1/2 times 1 would just be u to the 1/2. I have not integrated yet. All I'm doing is just trying to simplify my integrand. So now I'm ready to actually integrate. Add 1 to the 5/2 and I get 7/2. Dividing by 7/2 is multiplying by 2 7s. Add 1 to the 3/2, that's 5/2. Dividing by 5/2 is multiplying by 2/5. So negative 2 times 2/5 is negative 4/5. Add 1 and that's going to be 3/2. Dividing by 3/2 is the same as multiplying by 2/3. All right. Then I can go through and multiply by 1/2. So 1/2 of 2/7 is 1/7. 1/2 of negative 4/5 is negative 2/5. 1/2 of 2/3 is 1/3. And then I need to back substitute and put 1 plus x squared back in the place of every one of my u's. And I'm finished.